Okay. Oops. Just a second. Oh, sorry about that. Something is not right. Oops. Oh, just a second. Oh, just a second. Hmm, just a second now. Something is not. Just a second. Let me. Oh, yes. Okay. Hmm, okay. Okay. Now, let us consider a very special case of the chain rule. So suppose that I have the function y defined by gx to the nth power. Okay. Then in this case, what is the outer function? Outer function f will be u to the n, the power function. And the inner function is gx. Then by considering the chain rule, if I want to differentiate this y function, you need to differentiate the outer function first. If I differentiate the outer function, you get n times u to the n minus 1. And then you multiply the derivative of the inner function. So you first evaluate the derivative of the outer function at the inner function, which will give you this, multiplied by the derivative of the inner function, which is g prime. Okay. So if I differentiate this function, you get this, the derivative of the outer function evaluated at g multiplied by g prime. And many students every year make a mistake with this g prime part. So whenever you have this power of a certain function, okay, so, or in other words, when you apply the chain rule, you must multiply the derivative of the inner function, g prime. So please remember this function. So here is another example. I have 100 power of x cubed minus 1. So what is the outer function? So the f of u, the outer function is u to the 100. So the derivative of the outer function will be 100 times u to the 99. So you evaluate this derivative of f prime at the inner function gx. So that's this term comes from 100 times x cubed minus 1 to the 99th. And then you must multiply the derivative of the inner function. You must differentiate the inner function and then multiply the result to the previous term. So the derivative of the inner function is 3x squared. So you need to multiply that term to the derivative of the outer function. So this is the final answer. Okay? So this is the result, the derivative of the composite. So before we consider this, let me consider some more examples. So one more thing. If I have the product of two functions, so when two functions f of x and gx are multiplied to define a new function, then when this product is differentiated, you need to differentiate one function at a time. So f prime of x times gx plus f of x g prime of x. If you happen to have the product of three functions, say f of x times gx times h of x, then when it is differentiated, you need to differentiate one function at a time. So you first differentiate the f prime without changing the other two. And then you differentiate g function without differentiating the other two. And then you differentiate h function, but you do not touch f and g. So this derivative goes to the first term, second term, and the third term. And when one function is differentiated, the others are not changed. However, in case of the composite of two functions, f of g of x, when this is differentiated, so okay, you get the derivative of the outer function evaluated at g function multiplied by g prime of x. If you have the composite of f of g of h of x, when this function is differentiated, you first differentiate the outer function, which is f. So f prime evaluated at the inner function, and in that case the inner function is g of h of x. So this is the derivative of the outer function evaluated at g, the inner function. And then you need to multiply the derivative of g of h of x. Okay, so the derivative of the inner function will introduce another chain rule. So that is g prime of h of x multiplied by h prime of x, because this inner function is another composite function. So when g of h of x is differentiated, you first differentiate the outer function g evaluated at h, and then you need to multiply the derivative of the innermost function, which is h. Okay, so this is what you get. So here is some example. If I have a product of two functions, say if you have e to the x multiplied by x squared plus 1. So in that case, I have a product of two functions. When this product is differentiated, you need to differentiate one function at a time. So you differentiate this e to the x and then multiply x squared plus 1. And then it's time to differentiate x squared plus 1 while you do not touch the first one. In case of exponential function, the derivative of e to the x is e to the x. So and then when x squared plus 1 is differentiated, you get 2x. So e to the x is common, so x squared plus 1 plus 2x. So that will be the final result of the differentiation. If you have the composite e to the x squared plus 1, we have a different story. Okay, that is the exponential of x squared plus 1. So the derivative of the outer function, the e to the x, has the derivative of e to the x. So the derivative of the outer function is still the exponential function. You evaluate that exponential function at the inner function, x squared plus 1. But that's not the end. You need to multiply the derivative of x squared plus 1, the inner function. So you need to multiply the derivative of x squared plus 1. So you get e to the x squared plus 1 times 2x. So that is, okay, the derivative of e to the x squared plus 1. Please be careful. So in case of the first example, e to the x times x squared plus 1, for the derivative of that product, you need to apply the product formula. For the next example, you are considering the composite of two functions. So in that case, you need to apply the chain rule. So please be careful. When two functions are multiplied, you need to apply the product rule. When you consider the composite of two or more functions, you need to remember the chain rule. So please remember this. Okay? Now, previously, in case of the derivative of the exponential function, we had this formula. When this b to the x is differentiated, we get b to the x times what? The, okay, no, not this one. So I didn't consider that one yet, so let us consider this slide. Okay, so I want to consider the differentiation of this b to the x, but b to the x, okay, we do not know this one yet. Okay, so actually the other day so when f of x is given by the exponential function, then we derived this. The f prime of x was f of x times f prime at 0, right? So that's what we learned the other day. That's what we could derive. And since we do not know the derivative of this function at 0, we considered a special case only, right? We considered the special case e to the x, so that f prime at 0 was 1, and that comes from the definition of e, right? So in that case, f prime of x is equals to f of x. In other words, the derivative of the e to the x will be e to the x. That's what we could derive, right? So now, in this case, in this section, we want to consider the general situation, the b to the x. But since we do not know this formula, okay, yet, but we could apply some formula regarding the exponential function. And in case of the exponential function, we have several theories and properties like this. As I said, if I have a to the, actually we, regarding the log of b with c with the base b, and I told you that that is the same as c with log a with base b. So one property of the logarithmic function is that you can switch this a and c without, okay, and we have that formula. So b is b to the 1, and that is b to the log e with the base e is 1. In other words, b is the same as the b ln E. Okay, and as I said, in that case, this B and E can be switched. So if I switch, you get e to the ln b. That is the same as b, and that comes from this formula of the logarithmic function or exponential function. Oops. Oh, why? Okay, just a second. Let me just a second. Just a second. Where's your? Where's your? I got one note. So, okay. Okay, I got one note from one of the students asking if it is possible to access my recorded lecture. And I have the video recording. Yes, I do have them. But the problem was this: when I make those video recording available, that then that many students were attending the classes, and they were not, they some students thought that they would watch the video recordings later, but they didn't do that, and then they didn't follow the notes at some point. And so that's why I do not want to distribute the video recordings, because I have many pros. I don't have, okay, I have many, not I have, but students have many disadvantages eventually. They say they would watch the real-time video recording, and they say they would watch the video recordings as well, but they made promises, but eventually after the midterm they do not watch any of these. So that's why I'm hesitating to distribute the video recordings. So let me think about it, okay, a little bit, and then let me announce that later, okay? But anyway, that was the answer to some students. Okay, and what is the problem with this, my program? Uh, okay. Okay, so so any b can be written, I mean any positive b can be written by this, right? So if that's the case, so if b can be written as e to the ln b, then b to the x is the x power of this exponential function. Then, as you know, e to the a times b will be e to the ab, right? So x power of lnb will be e to the lnb times x. So please note that lnb is a constant. So this is a constant. So I have some exponential function, but the exponent is not x, but constant multiple of x. Okay. So differentiation of b to the x is eventually the same as the differentiation of this exponential function. Now, I want to look at this expression inside the parenthesis as the composite of two functions. So that is the exponential function of ln b some number multiple of x. So what is the outer function? The exponential function. What is the inner function? Constant multiple of x. So if I differentiate the outer function, we get the exponential function. Evaluated at the inner function will be this. And then I need to multiply the derivative of the inner function. And the inner function is just a constant multiple of x, right? So if I differentiate this in x, you just have the constant function. And e to the ln b of x was initially another form of b to the x. So when I differentiate b to the x, you get b to the x times ln b. So this is the final formula you have for the differentiation of the exponential function. When b to the x is differentiated, you get b to the x times ln b. Okay. So let me repeat this one more time. So as I said, please remember we have if I have a log c with base b, then I can interchange a and c. If I switch a and c, you get this, okay? For any positive a, b, and c. So as a special case, when b and c are both e, then I have a to the log e over e equals e to the log a with the base e. Log with the base e is just a natural logarithmic function, ln function. So in other words, a to the ln e is the same as e to the ln a. But note that ln e is just 1. So that means I can erase this. Okay. And because ln e is just the value 1. So for any number a, we can rewrite this a as e to the ln a. So for f of x defined by b to the x, b can be written as e to the ln b. So b to the x is the x power of this e to the ln b. So we have e to the ln b times x. That is that's the same as b to the x. That is the same as my function f. So if I differentiate b to the x, I'm differentiating the exponential function of ln b times x. So this exponential function is the outer function. So you differentiate the outer function. If you differentiate the outer function, you get the same e to the x function. So you have ln b times you evaluate this derivative at the inner function ln b times x, and then you need to multiply that by the derivative of the inner function. The inner function is a constant multiple of x, like 2x, 3x, 5x. So if you differentiate this 2x, you get 2. If you differentiate 3x, you get 3. So if you differentiate this log b times x, you get log b, right? And this e to the ln b of times x, that is just b to the x. So if I rewrite this, you get b to the x times ln b. Okay, so that is the formula. That is the differentiation of b to the x. Okay, and when b is e, ln b will be ln e, which is 1, and the formula becomes e to the x, derivative will be e to the x. Okay, so but that was already derived the other previously. Okay, and today we learn how to differentiate this b to the x function. All you have to do is you need to multiply one additional term, ln b. So if I consider this e to the x function, when I differentiate e to the x, you need to multiply ln b, and b is 2 in this case. So if you differentiate e to the x, you get 2 to the x times ln 2. Okay. Now, if I have this, okay, if I have this, then this is the composite function of 2. So this is the composite of 5 to the u function and x squared function, right? So if I differentiate h function, you need to remember the chain rule. So if I differentiate this h, then I'm differentiating this composite function. You first differentiate the outer function. So the derivative of the outer function evaluated at the inner function x squared multiplied by the derivative of the inner function x squared. So what is the derivative of 5 to the u function? As we studied, we get 5 to the something, 5 to the u times ln 5. So that is the derivative of the outer function, and you evaluate this outer function at the inner function, x squared. And you multiply the derivative of the inner function, which is 2x. Okay, so the derivative of h of x will be 2 times ln 5 times, this is a constant, and you have x, and then 5 to the x squared term. Okay, so this is your final answer as the derivative of h of x. Okay, and here is one description regarding how to prove the chain rule. So if you are interested in, please read this yourself. And but we are not going to consider these 2 slides in our class. Okay, so yeah, that was the end of this section, and in this section we just considered how to differentiate the exponential function in general. Okay, now we want to consider, which is very interesting and which may be useful in some situation, okay, which is called implicit differentiation. So far, when we consider the derivative of a function, we considered a differentiation of certain function when its definition is given, like some function, say square root of x cubed plus 1, or a product of two well-known functions. Those are given as the definition of the function f, right? Then based on the shape of this definition, we could apply the chain rule, we could apply the quotient rule or product rule, right? Depending on the situation. But sometimes functions are defined implicitly, meaning, let us consider this equation. X squared plus y squared is 25. Now, if I consider some specific value of x, say when x is 0, then the y value will satisfy this equation, and you can derive the explicit value of y, say y will be plus or minus 5. When x is, say 4, I'm sorry, say 16, no, x is 4, yeah. So when x is 4, then x squared will be 16. Then the equation will become 16 plus y squared is 25, so that y squared will be 9, and the value of y will be plus or minus 3, like this, right? So, which means the value of y can be found once the value of x is given, or vice versa. When the value of y is given, the value of x can be found, and the value of y is affected by the value of x. When the value of x is changed, the corresponding value of y will be also changed. So in some sense, this y is affected by the value of x. In other words, the variable y may be regarded as a function of x. Okay, so when x and y are appearing in one equation, as in equation number 1 or equation number 2, okay, and the value of x affects the corresponding value of y, then we say y is an implicit function of x. Okay, so equation 1 and equation 2 define two implicit function. Okay, but in this equation, if you want, you can derive an explicit relation. So these are called, in these two cases, we say y is an explicit function of x, and in these two cases we say y is an implicit function in x. Okay, so that's the difference between the explicit definition and implicit definition. So in case of the explicit definition, we have this expression, y is something in x. So only some expression in x. In that case, we say y is an explicit function in x. But if x and y are somehow related within some relation, as in equation 1 or 2, we say y is an implicit function of x. Now, in case of number 1, even though it is implicit, y squared can be represented by 25 minus x squared. So y will be plus or minus square root of 25 minus x squared. In other words, one implicit function introduces two explicit functions, right? So y equals to the square root of 25 minus x squared, and y equals negative square root of 25x squared. Anyway, the point is, given this implicit relation, I can derive some explicit definitions in case of number 1. In case of number 2, it is a little bit difficult to derive explicit relation. Okay, so we will go back to this expression later. Okay, so probably after the midterm, we will consider this example one more time. X cubed plus y cubed equals 6xy, and somehow we want to derive some explicit relation, okay, from this implicit relation. But we need to study some technique for the second equation. But anyway, the point is that if you have an implicit relation, you can go back to an explicit relation easily, but sometimes that may be challenging or almost impossible. But why do we consider the differentiation? We want to find the instantaneous rate of change of certain function with respect to another variable, right? So given this implicit relation between x and y as in equation 1 or 2, if we want to find the instantaneous rate of change of the variable y in terms of x, then we need to consider some differentiation. Okay? And in that case, you do not have to derive an explicit differentiation when you want to find this rate of change. All you have to remember is that this y is some function of x. Okay, so when you differentiate this, so let me skip this. So we will go back to this figure 2 later. Okay, but I don't want to bother you with this. So the point is, we don't need to solve an equation for y in terms of x in order to find the derivative. In other words, if we are interested in the instantaneous rate of change of y with respect to x, okay, you don't have, so that part, this, we don't need to solve for y in terms of x. That means we do not need an explicit form of the y variable. We do not need. All you have to do is you need to remember that this y is somehow related with x. And for this somehow in mathematics, we say y is implicitly related with x. And that means, okay, so when y is an implicit function of x, then it is still a function. So all you have to do is, okay, y is a certain function in x. So when this function is differentiated, you need to remember that fact. So for example, when I consider this equation, and if I want to find the derivative of y with respect to x, I have y squared. Then y is a function in x variable. That's y. And I have this function squared. And I want to differentiate each term in x variable. Then, okay, when I look at x squared, I can easily differentiate this x squared with respect to x. That will be 2x. But how about this one? If I have a square of certain function in x, then I have some function in x and that is squared. Then that is a composite function. And if I want to differentiate a composite function, I need to apply the chain rule, right? So given this equation, if I differentiate each term in x variable, when I differentiate x squared, that will give you 2x. Now, for the next term, you need to remember that this y is a certain function in x. Even though it is defined implicitly, it is somehow a function in x. And now I have its square term. So what is the, and this is the composite. So what is the outer function? Outer function is the square term, right? And what is the inner function? Y, right? So f of u is u squared and g of x is y. So that y squared is the composite of these two, right? Even though we do not know the explicit form of g, that's the composite. So for the derivative of y squared, I first differentiate the outer function, u squared. When u squared is differentiated, you get 2 times of u, and you evaluate this derivative at the inner function, y. Right? So this is the derivative of the outer function evaluated at the inner function. So this is the derivative of this u squared function, outer function, evaluated the inner function y. And you must multiply the derivative of the inner function. What is that? dy dx. Even, okay? And that must be the derivative of the right hand side. The right hand side is 25, some constant. If I differentiate their value with x, then you get 0. So we have this equation, right? So I have 2x plus 2y dy dx is 0. Now at this point, this term has a dy dx while 2x does not have dy dx. In that case, please move these terms without dy dx to the other side. So we get 2y dy dx is negative 2x. And then please divide this equation by this term in front of dy dx. So dy dx will be negative 2x over 2y. And I can cancel 2 and you get negative x over y. So that is the dy dx. That is the instantaneous rate of change of this function with respect to x. Okay? That is the slope of the tangent line when certain point on the graph is given. Okay? So let me go back to this slide. So if I have an implicit relation And then you can consider, and if you want to find the dy dx, you can consider implicit differentiation. That means if I have the equation defining some implicit relation, please differentiate this equation you need to differentiate the both sides of this equation with respect to x, and at that point you need to remember that y is a function of x, even though we do not know the explicit definition of this y, but we know the fact that this y will be some function in x. Okay, so that term, when y is differentiated in x, that differentiation will introduce a dy dx. So this part will introduce dy dx. Okay, so when you differentiate both sides of the equation with respect to x, some term, especially terms those having y, will introduce a dy dx. Okay, and then you need to solve the result for dy dx as I did moments ago. So that will give you the derivative. Dy dx is y prime, or the f prime of x. Right? So even though we do not know f, we can still find y prime. That is the rate of change of this y with respect to x variable. Now let me go back to the example again. So in this example, if x squared plus y squared equals 25, the first question was to find the dy dx, and then the second question was to find the tangent line to this curve at this point, 3 and 5. So when x is 3 and y is 4, you want to find the equation of the tangent line. So we have the formula for the slope of the tangent line. The equation, the slope of the tangent line is negative x over y. So when the point is 3 and 4, x is 3 and y is 4, at that point dy dx, the slope of this tangent line, will be negative x over y. X is 3 and y is 4. So that means the slope of the tangent line will be negative 3/4. And I know that this tangent line will go through the point 3 and 4. So using this, okay, so I could find the dy dx, and since x and y are given, I could find the specific value of the slope of the tangent line, and I know that the line goes through 3 and 4. So if I combine these two, find this equation, y minus 4 equals to the slope times x minus 3. So eventually you get this. So this is how you find the tangent line. Now, if you want, you can go back to the explicit definition. From this equation, you can find this equation that will define the one function for the upper semicircle and one for lower semicircle. And please remember that 3 and 4 are points on the upper semicircle. So we will play with this one. Okay, so given this, I can differentiate this function with respect to x using the chain rule. Given this expression in x, I can plug in 3 and 4 to get this slope of the tangent line and find the same answer. But you don't have to derive this explicit relation. You can just play with implicit relation. Okay. Anyway, let's call it a day here, and let me continue on Wednesday, read a little bit more examples. Okay. Thank you for listening, and see you on Wednesday. Okay. Bye.